Hi, Rob. Rob? Hello? 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 Hey, Rob.
Hey, how are you?
Good, good. Oh,
Good.
you have a good background.
Yeah, it's Berkeley. Yeah.
What? Oh, that's your desktop background?
No, it's my college, right? A Zoom background.
Oh yeah, I don't know how to get the background. I heard about it.
Yeah.
From
If you go to video and then click on the menu there, they might give you an option. Yeah.
video
hmm
menu with
Go
bottom
to
or
like
bottom
yeah
or
on the bottom. On the bottom, go to your video. There should be an arrow next to your video icon.
I don't have video icon.
Some versions of Zoom don't have
Oh,
it.
start a video.
Yeah.
Oh, start a video. Yeah.
Yeah. Yeah.
Choose virtual background. Okay.
Yeah.
Okay. But anyway, I don't need to present myself actually.
Okay.
How's your kids?
Yeah, everyone's doing good. We're actually going on vacation Monday. So,
Vacation at this time? Where?
well, it's the only vacation I've taken in like, I don't know, 7 months. We're going to Appalachian Mountains. Yeah. So we have an Airbnb and
Air at this
yeah,
time?
we're
You
going to be in the woods. I know, I know. I hope it's clean, but it'll be okay, I think. Yeah.
are
At,
you-
at Fannie Mae, do they ever talk about going back to the office or?
yeah, right after Labor Day.
Oh,
Sometimes
okay. That's the plan.
September 8th. Yeah, it's already laid out earlier, very earlier. So
Okay.
people already get that prepared, and yeah.
Yeah.
So at the beginning, we will start with 30% of people
Oh, okay. Okay.
volunteer. So I'm not gonna volunteer. Right?
It's the same thing at FI. Right now is optional. So I was going, but then nobody else was going. So
That's cool, right?
yeah, yeah. But then I thought, what's the point? So I just stopped.
Well, you can stay away from kids, right?
Yeah, I guess.
I mean, honest, I think kids are very annoying.
It is
Like,
very hard to work. Yeah, because they cannot not bother you. They can't help it. You know what I mean? Yeah, they're always coming in and yeah.
Hey, Robert. Good to see you. This is Richard.
Hey, Richard, how are you?
Good, good.
Yeah.
Thanks for sharing, for coming and wedding being,
Yeah, I mean,
here.
it worked out because we just posted this topic on our website, so it's very top of mind. So I have no problem presenting it. So it's
Nice. So
yeah.
you mean you post this topic on FI's website?
Yes, yes. So
Cool.
if you want to learn more, you can download the full paper. hmm
So you mean a conference paper or it's a white paper?
No, it's more like like a white paper.
Okay,
7 pages. It's not an academic paper. No.
cool.
Yeah. Yeah.
Hey, Robert. Yeah, this is Simon, Ji Dongzhang. Yeah, Robert, thanks for
Oh,
giving
yeah.
the talk soon.
Of course.
Oh, Rob, you met Jidong before? Simon?
I'm not sure, Rob. So, Rob, so you work for FI Consulting, right?
Yes.
Yeah, I work for Wells Fargo. I'm not sure. Maybe your team helped us before, maybe not. But I think Ken mentioned you many times. Great.
Yeah, yeah. Are you in Wells Fargo in Virginia or
I'm in Tyson Corner office.
Tyson's Corner? Okay,
Yeah.
great. Yeah, I think we had some model validation work there like a few years ago, but not recently.
Got that. Yeah, I joined Wells about 5 years ago, but I know we typically not so many consultants. Maybe that's maybe several years ago they have some engagement. Yeah.
Yeah. Do you know Agus Sujanato?
Sure. Yeah. He's
Yeah.
the head of our validation. He's based in Charlotte.
Right. I met him at a lot of conferences. He's always speaking. And
Oh,
yeah, that guy is just, he's amazing. You know,
yeah.
I always read whatever he has to say about machine learning or.
Really? That's a
Yeah,
lot.
yeah,
That's
yeah.
too much.
Yeah. Very, very academic and very just, yeah, he's very smart guy.
Yeah. I think that's his major when he started his PhD program. So he is very he have a lot of passion on that.
But I mean, are you guys implementing that stuff at Wells Fargo like day to day, or is it more, you know? Yeah.
We have pretty big validation team. One of the team actually dedicated for that. So internally we have a lot of research, paper publication. Even within the team, they share some kind of most progress. Yeah, we do have.
Yeah, that's great.
Mm. Ken, do we have?
I probably sent out the wrong access information today to all the attendees.
Can't just send a correction. That was just
Okay.
a reminder.
Oh yeah,
The original one was correct. You said the one you sent out yesterday was right.
right. Yeah. Ah, that's.
Hopefully, most of people would use the original email, but you can just quickly resend with the right access information to the same group. We still see many people are coming joining us.
How can I reply to the same email? Maybe.
Yeah, because you BCC'd everyone, so like.
Yeah, and then I cannot reply to that because I sent it, right?
Okay.
So,
But Ken, if you are the sender, so you should have ability to reply all or something like that, right? So you should have everyone.
in Gmail, I don't see that option.
No, you go to the sent mailbox.
Yes, I've already opened it.
Right. Copy all the BCC.
How can I copy BCC? Oh yeah, hold on. Yeah, I got it.
Okay. Ken, do you think we can start while you're resending the email?
Just 1 second.
We're 3 minutes over 2.
We're fine. I think we're fine. Just hold it for another 2 minutes, okay?
Okay.
Okay, sent. All right, yeah, we can start, Richard.
You want me to get started?
Yeah.
Okay, good. Good afternoon, everyone. Hello, Rob. I'm not going, I didn't mean to interrupt your drinking and get you choked. Thank you. Our pleasure to have you. I know we had this opportunity working together very shortly in the work, but I wish I would have more time to work with you, but I believe we will have more opportunity. But it's a great pleasure to have you this platform on this organization we call Chinese American Data Science and Engineering Association. It's a nonprofit organization we started last year, and we've been working together with Ken and with many other volunteers and as building up this community to share knowledge and enhance the career opportunity among the data science enthusiasts and professionals, as well as the students in schools, to build this platform for us to share a lot of skills and experience and knowledge in data science or related areas. So today we welcome everyone. So we see more than 20 people and still coming, more are still coming to join this online meetup. And I think it's a great, very interesting topic for many of us. So first, let me introduce Robert Chan. He is the Director of Model Development and Validation at FI Consulting. He is also FRM, which stands for Financial Risk Management. I believe it's a professional association for financial risk management. So he holds extensive experience in fixed income, currencies, and the commodities. Many experience in the trading and as well as data science and machine learning. So he's going to give us a interesting coverage on knowledge graphs for anti-money laundering and fraud detection. Thank you. It's all yours, Rob.
Okay, thank you guys so much for having me. Thank you, Ken. Thank you, Richard. I really appreciate it. Really excited to talk to everyone. Hopefully teach you a few things about knowledge graphs, which I think are a very exciting, area of data science. And yeah, let me just get into it. Let me share my screen because I have a slide deck. It says I cannot share. Yeah, it's a security feature of Zoom, I think. The host has to give permission. Yeah.
Take your time.
Oh, yeah, no, I can't share. The host has to give me the permission. Yeah.
Oh,
Yeah.
how can I grant you permission?
Yeah, I don't know.
Where?
Tricky. I've run into this issue before. It's like a new security feature. Zoom, yeah.
Ben, again, you will see security on the bottom.
Security. Yes.
Yeah, allow presentation.
Okay, cool.
Yeah.
Yes. Rob, you should
Okay.
be able to share now.
Oh, okay, super. Okay. Okay.
Nice.
See my screen?
Yeah, yeah.
Okay.
Yeah, I can see.
Okay, great. All right, so the title of this presentation is Knowledge Graphs for Anti-Money Laundering and Fraud Detection. So, anti-money laundering is a very important, issue, affecting banks. People, when they deposit money in the United States, for example, the regulation is that we need to make sure it doesn't come from an illegal source, so it's very important to, to track this. And we're going to see it's a very hard problem to solve. Okay, next slide. All right, so in the talk today, and I'll talk for maybe 45 minutes or so, and then we can leave 15 minutes for questions. We'll do a quick introduction to myself and also my company, FI Consulting. We're gonna just give a quick intro into graph databases, knowledge graph, in case you're not familiar with it. Then we're gonna dive into the topic, knowledge graph, specifically with the application for anti-money laundering, and then questions. Okay, so FI Consulting, we help clients drive business results through data, analytics, modeling, and technology. We're based in Arlington, Virginia. We have 75 plus employees. We have federal government clients and private sector clients. Our big clients include Treasury, SBA, USDA, the Federal Housing Administration. We do a lot of work in student loans for the Department of Education. Fannie Mae, Freddie Mac, our GSEs, and we do a lot of work at Capital One and Navy Federal Credit Union as well. Myself, I lead the model domain at FI Consulting, specializing in model development and model validation. Before I joined FI, and I joined about 7 years ago, I had 10 years career as a trader. I was trading FICC, fixed income, currency, and commodities. And I previously worked in London, Singapore, and Hong Kong. Okay, so let's talk about knowledge graphs. Some of you might know this already, but for those who don't, we can just do an overview. So a graph, in its most basic definition, is a structured set of meaningful relationships. A graph is a collection of nodes, and you can call the nodes vertices or points that are connected by edges. Okay, so each node represents some type of information in the graph, and each edge is a relationship between two nodes. So here we kind of have like the hello world, example for graphs, and it's based on movies. And we can see that we have a node, and it has a label called person, and then the node has properties. So a person could be Tom Hanks. And Tom Hanks was born in 1956, and that's a property of that node. And then we have a movie, which is another node, and the movie node has properties as well. The name of the movie, Forrest Gump, the release date, 1994. And then we have a relationship connecting the person to the movie, and that relationship is called acted in. And the relationship can also have properties. And and then we can also add other nodes that have different relationships. Like instead of an actor, we can have a director, and then we call that relationship directed. So, the basic idea is that we have different nodes, and they're connected by relationships. Okay, so, the simplest possible graph could just be one node, but, obviously we usually have more. And then we have labels, and a label is, like I said, either a person or a movie. And then the node can also have properties, 0 or none. Okay, So again, just kind of what I talked about before. You have people, you have movies, and you have properties. Okay, now the key idea behind knowledge graph are the relationships. And the relationships connect nodes, and that's how we find data that is related to a node. The relationships allow the graph to resemble a different kind of data structure. It can resemble a list, it can represent a tree, it can be a map, and those can be embedded and combined, and then we can form very complex interconnected structures. And then, like I said, the relationship can have a property. Again, we have person to movie, and the relationship is acted in. And then we have person to movie, and the relationship is directed. Okay, another key concept is traversal. Traversal is how you navigate your way through the graph and how you query the graph. And you start from any node you want, and you can find related nodes through the relationships. So the relationship can be traveled in any direction. Even though I showed you have an arrow, person to movie to denote the acted in relationship, you can actually, traverse in both directions. So let's say you want to start from person, and then you want to find what movies, the person acted in. That's called an outgoing relationship. Let's say you want to start with the movie, and then you want to find out which actors were in the movie. You also traverse the acted in relationship, but you travel in the opposite direction. Okay, so traversing a graph means visiting the other nodes and then following the relationships according to certain rules. Okay, so it's a good idea to talk about knowledge graph in relation to what most of us are already familiar with, which is a relational database. The key difference is that in a graph database, the main idea is that we have the relationships, which you do not have in a relational data store. So here we have a relational database example, and it involves people and at a university, and the departments that are connected to those people. And so if we wanted to find person Alice, who has person ID 815, the way we do it in the relational world is that we go to the person table, which is in green, and then we join to another table that has ID and department, and then we join to another table that has the department and the name of the department, and that's how we find out what departments does Alice belong to, okay? Now, let's do it in the graph context. Okay, so in the graph context, we still have Alice, and Alice is part of a person node. Alice will belong to 3 different university departments, so we create a node for each department that Alice belongs to, and then we connect the nodes back to Alice with a belongs to relationship. So, we're getting the exact same information, out of our database, but, the data is structured in a different way. And again, like we're not saying that one is better than the other. It's just different ways of organizing the data. And you'll find that if you organize the data differently, there are advantages, to doing it that way. Okay, so a relational database is optimized in a certain way. It's optimized for aggregate data. A graph database is optimized for connected data. So if you want to navigate very deeply through a relational database, you have to do a lot of multiple joins. And multiple joins, come with costs, and they can be expensive performance-wise. A graph database is great for returning a very deep relationship. And we illustrate that here with these kind of examples of the A table, the B table, and the C table. And you can see on the right, if we want to know that B2 is connected to C3 and A1, you have to do a lot of table joins in the relational database world to understand that information. But in the knowledge graph context at the bottom, you can see that because we explicitly define the relationship between B2 C3 and A1, it's a much easier, query, to make, because we've already embedded these relationships into our graph. Again, it's not saying one is correct or incorrect, but it's just a different way of organizing the data, depending on what it is you're trying to do. Okay, so here are some use cases. Graphs are used to model many different types of relations and processes, and they have applications, the applications are really endless. I think a lot of you are familiar with, a lot of the big, tech companies out there use graphs as a major part of, their technology. Google, for example, their original algorithm for search, PageRank, is based on graph theory. Obviously, any kind of e-commerce company like Amazon, they use graph theory to recommend different products to you. Facebook, obviously, LinkedIn, Netflix, when you watch a movie, that's how they, come up with the other ones to recommend to you. A lot of it's based on graph theory. So you can see that the example is online retail, media and broadcasting. It can be for logistics or enterprise resource planning. You see on the bottom right, it's a network, like a, infrastructure network, organized in a graph, recommending shortest paths, optimal routes, increasing efficiency. So the applications for graph theory are really endless. Okay, so we're going to talk specifically about anti-money laundering. Okay. And anti-money laundering is a very difficult problem, for banks to solve. The reason why, money laundering, if you're not familiar with it, the people who do money laundering, they try to hide it, obviously. And the way they do that is through what's called account layering, meaning that they like to make a lot of different transactions to kind of cover up, what it is they're doing. So a fraud, can be very complicated. And it's very hard to separate, okay, what's a non-fraudulent transaction and what's a fraudulent transaction. And you can see that it just becomes like a web of a lot of transactional data, that we need to sift through. So to combat fraud, we need to, find a way, to efficiently, navigate all this data. And we need to, somehow classify what is a fraudulent transaction and what is a legitimate transaction. So here, we just have an example, illustrative example of what a graph might look like. And then you have, different nodes representing different things. A node can represent the name of an account. It can represent a social security number. It can represent a credit card tied to the account, a bank account, a loan type. The possibilities are really endless. And then we have relationships that connect all the nodes. Telling us what nodes are related to which other nodes. Okay, so in the traditional anti-money laundering, construct, and the way that most banks, do it now, is they don't use a knowledge graph. They use what are mainly, rule-based, type methods. And what they do is they have rules saying, if I transfer my money, 5 times in a day, I flag that, right? Because that's very suspicious. And I flag, large amounts of money. I have like, a list of suspicious people, suspicious countries. If I'm doing business with a country known to engage in terrorism, then I'm flagged. So, currently it's very rule-based, and that's the way the majority of the banks, do fraud detection today. However, there's kind of an issue with that. And the issue is that these money launderers are very, intelligent, and they figure out what the rules are, and then they'll do something different, to evade the detection, right? So by the time you find out what the fraudulent, behavior is, the fraudster has already moved on and is doing something else. Okay, so, there are obviously deficiencies in this approach. So why are there deficiencies? Financial networks are global, they're complex, they're high dimensional, and they're very nonlinear. if you have like a simple rules-based approach, it doesn't scale well, and it will produce a high rate of false positives. So what do we mean by that? A lot of things are going to look like fraud, but they're not fraud, right? I mean, I know from personal experience, when I get a call from the bank, and I know I'm not doing anything, bad, it's because their detection is very, too sensitive. So producing a lot of high false positive rates. What I mentioned before, the fraudulent behavior is deeply hidden, behind a lot of innocent transactions due to this account layering. And then, again, like I said before, if your detection system is based on identifying a historical pattern, you're not going to find a new pattern until it's too late, basically. Okay, so the great thing is that the regulators have caught up, to this issue, and they're trying to encourage all the banks to, step up their efforts to combat money laundering. And they encourage banks to employ innovative approaches, artificial intelligence. They recognize that financial institutions need to become more sophisticated in their approach. And they're encouraging, financial intelligence units to identify more complex, vulnerabilities and threats. So they've really given the banks a lot of, permission, to explore, complicated AI, to solve this problem. Okay, so how do we represent this, money transaction monitoring, system in a graph? Okay, and there are many ways to do this, but here's an example how. You can have people, you can have bank accounts, okay, and then you can have the relationship showing which person owns a bank account. You can have relationships from bank account to bank account showing how much money was transferred, the date of the transfer, so on and so forth. You have properties, the name of the person, what country they're from. So all this information is, embedded in your graph, okay? And then, what we're showing here is a very tiny piece, obviously, of the graph, but you can imagine how many transactions that banks have, every single day and how many customers they have. So this will get very high dimensional very quickly. And we're going to have thousands of relationships between thousands of entities. And it's really something that you need a very efficient, system, to really work through. Okay, so let's talk about some key concepts here. The key concept for detecting fraud is what we call connectedness. And what do we mean by that? Okay, so we want to identify which nodes are close to other nodes, okay? And then we want to identify communities, all right? So it's like Facebook. If you have a friend and you have another friend and your two friends happen to be friends with each other, that's a community, right? Because you know someone else, and they know each other as well. This is behavior that we want to detect, right? And then we have a concept called ranking. And that kind of means that, again, going back to the Facebook example, if I have a friend and my friend is a really, trustworthy, person, if I'm their friend, then maybe that means that I'm very trustworthy too, because the idea is that, people that you're connected with, people that you're close to, you're very similar to, right? So you have a concept of ranking as well. So these are kind of like the core principles that we have, for utilizing graphs, to get information out of them. And so we're going to talk about two specific techniques. And the first one we're going to go over is clustering. And the second one we're going to go over is label propagation. Okay. All right, so we have an example here, and we're going to use this example, for both clustering and label propagation. It's a very simple example, but it illustrates a general concept. We have nodes here, and we numbered them, but the nodes could represent anything. They can represent customers, they can represent bank accounts. This is dependent on your data, right? How you want to label these nodes, okay? And for example, they could be entities of financial institutions. How do we know these financial institutions? Well, every bank does what's called KYC, know your customer. So we have some basic information, about every account, address, country of origin, things like that. And then how do we know how different nodes are connected? Well, we know because we have basic transaction data, right? When a money transfer is made from one node to another, we have records of that. And then we have what are called SARs, suspicious activity reports. So if I go to my bank and I deposit, more than $10,000 in cash, then they fill out an SAR, because any amount over $10,000 could be money laundering, something like that. It doesn't mean you did anything bad. It means that it's just a record that they have on file, that all banks need to fill out for large transactions and things like that. So we have some information about, the different, types of activities going on regarding money transfers and things like that. Okay, so let's start with clustering, okay? So we're gonna use what's called spectral clustering. And what this algorithm does, it uses the information from the eigenvalues of a matrix that is built from the graph. And then what we're gonna do is we're gonna construct these matrices, we're gonna interpret their spectrum, and we're gonna use the associated eigenvalues and eigenvectors to assign our data to clusters. Now, there are different ways to do clustering. If you're into machine learning, there are lots of algorithms out there, like k-means clustering and things like that. Now, what I like about spectral clustering is that it has a very, very, it's rooted in a very sound, academic theory. Now, the thing about k-means, and there's nothing wrong with k-means, but you have to make certain assumptions with k-means. Like you have to assume how many clusters am I going to have? Like that has to be a user input. And then k-means is it's a simulated algorithm. So you actually have to run k-means several times to make sure that you're converging on the right result. So nothing wrong with k-means, but I believe spectral clustering is more, it's just more grounded in theory, and there are less assumptions that you have to make. Okay, so spectral clustering. From the graph that we had, we build what's called the adjacency matrix, okay? So in the adjacency matrix, the rows and the columns represent our different nodes. So if you go back to the graph, you can see that we had 11 nodes. So we have an 11 by 11 matrix. And then row 0 is our first row. And then we have a 1, in the coordinate of 0, 4, okay? Right. So that means that 0 and 4 are connected. So let me go back here. Let me hope that's correct. Yes, it is. Okay. So if you go to node 0, you can see it has one edge, and the edge is connected to 4. So we put a 1 there. Okay. So then now if you go to the second row, which is node 1, we have a 1 for node 3 and a 1 for node 4. So that means that 1 is connected to 3 and 4. So let's go back and check that, and yes, it is, okay? So we build our, our full adjacency matrix in this manner, all right? So it just shows which nodes are connected to other nodes.
Hey, Rob.
Yes.
Quick question. So it looks like here you only have one indicator of the relationship. So you cannot differentiate what type of relationship they are, right?
Yes, very good question. It doesn't have to be a 1. It could be a probability signifying the strength of the relationship. For this example, we're making it easy. We're just saying that every relationship is a 1. But no, that's a great question. These can be probabilities. They can be something less than 1. And that's definitely something that you might want to do. Because we're kind of making the simplifying assumption that every node has the same strength relationship to any other node. Which will make it easier for this example.
I see, that makes sense.
It might not be the case.
Thank you.
Okay. Node 1 had 2 connections, so we put 2. So the degree is simply adding up the rows in the adjacency matrix. And then it's a diagonal matrix where you have, the number of degrees along the diagonal, and then every other entry is a 0, right? So that's the degree matrix. Okay. Then we construct what's called the Laplacian matrix, okay, from the adjacency matrix and the degree matrix. And the formula is there. It's simply, D minus A. That's all it is. And this is called the normal Laplacian. And this matrix has a lot of special properties. And we're going to work with this matrix to do our clustering. All right. So we then find the eigenvalues and eigenvectors of the Laplacian matrix. All right. And we can plot the eigenvalues here. And we plot them in ascending order. And the number of 0 eigenvalues tells you how many connected components there are. So a connected component means that there's no separation between points, okay? And if you go back, you can see that, we have a connected graph. Every point is connected to every other point. There's no separation of two groups or anything like that. So that's why our first eigenvalue is a 0, all right? And then the magnitude of the eigenvalues tells you something about the density. Okay, if we had a very densely connected graph where different nodes were connected to a lot of other nodes and there was more connectivity within the graph, we'd have higher eigenvalues. That's kind of the extent that I can explain. This is a very, deep subject of, this kind of theory, linear algebra, things like that. And I definitely encourage you to read more about it to get a better understanding of what the eigenvalues and eigenvectors signify. But there are some, rules of thumb that we can deduce, from the eigenvalues. Okay, so the first non-zero eigenvalue is a special eigenvalue, and we call that the Fiedler value. Okay, the Fiedler value approximates the minimum graph cut needed to separate the graph into 2 connected components. All right, so what does that mean? So if you look at our second eigenvalue, it's a non-zero eigenvalue, and it's a number very close to 0, but it's not 0, all right? Now that tells us that the graph could easily be separated into 2 connected components, okay? And the reason why is that we only have, you can kind of see intuitively there are kind of 2 groups, right? And if we were to cut the graph, right where the node 5 is, we would have 2 totally separate, graphs. And it's very easy to do that because we only have one link, 6 to 5, that's connecting these 2 groups. Now, if we had more links, then the Fiedler value would be a higher eigenvalue. But again, that's kind of like the rule of thumb, because our Fiedler value is very close to 0. That means that it's very simple to separate this graph into 2 connected components. All right. All right. Then we find the associated eigenvector corresponding to the Fiedler value, and that's called the Fiedler vector. And the Fiedler vector is here, so you can look at it. And every value in the Fiedler vector gives us information that if we were to cut the graph into 2 connected components, which side of the cut will the node belong to, okay? And you can see here that, 0, 1, 2, 3, 4, 3, and 4, they're negative, and they have roughly the same value in the eigenvector. And then you have 6 through 10, and they're all 0, okay? And then we have this value in the middle, that's kind of not really 0, not really like the others, just kind of in the middle, and that corresponds to node number 5, right? So we use this information to tell us that there are clusters, essentially. So it's telling me logically through the values of the Fiedler eigenvector that, nodes 0 to 4 belong to one cluster, and nodes 6 through 10 belong to another cluster, and it's saying 5 is kind of ambiguous, you know? It's a bit closer to 0 to 4, and you can see that intuitively, you know, just by looking at the graph. But it could also be grouped in with 6 through 10 as well, right? So this information is telling us what, you know, what we expect, right? That, you know, 0 through 4 are, you know, on one side, and they can be called a cluster. 6 through 10 are on the other, and then we have node number 5, which is kind of in the middle. It could belong to either one. So that's exactly what the values of this, you know, eigenvector are telling us. Okay. Now, okay, this is just kind of repeating what I just said. Now, you know, that created 2 clusters. Now, let's say you want more clusters, then all you do is you take one cluster and you just simply repeat the process. Okay. So, you know, I've now separated 0 through 4. I can do this spectral clustering again. If I want to find out what is, you know, my cluster within that cluster, I can do it again for 6 through 10. And I just continue on in this way until I get as many clusters as I think are necessary. All right. So that's a great way to do clustering, you know, through knowledge graph. All right. Let me pause there. Does anyone have any questions about this spectral clustering? Okay, well, if you have a question, you can ask me later or just put it on the chat. Okay, let's move on to the second example, and that's called label propagation. Okay, now label propagation is a semi-supervised machine learning algorithm. All right, so you have unsupervised learning where you have no labels, where it's kind of like exploratory analysis. Like we don't know how to classify our records, all right? So it's called unsupervised. And then you have supervised learning where you have labels where, you know, okay, I know, you know, number 1 is a fraud, I know number 2 is not fraud, et cetera, et cetera. And that's called supervised learning. So label propagation is called semi-supervised. And what that means is that I know something about some of the nodes, but I don't know about all of the nodes. Oh, I think someone's putting something on the chat. Oh, okay. All right, we're talking about graph databases. Okay, I purposely didn't talk about any kind of specific product. There are many on the market and new ones are coming out all the time. I think Neo4j is the best way to get started. That's how I learned. It has a very friendly user interface. It's free. Anyone can download it and get going. They have great examples, great tutorials. I think Neo4j is great. However, at FI Consulting, we don't use Neo4j. We use different graph databases, and I'm not really the expert who does that. We have another person who's kind of the product expert, and he uses Cambridge, Anzo. There's another one that's native to AWS, I believe, and it's called OrientDB. There's another company called Stardog that has really good software for graphs, and a lot of them are using there are standards in the graph world. And again, I'm not really the expert on this. You know, my colleague is kind of the expert for how to ingest information into a graph. But there's a standard called RDF. And RDF is kind of like, you know, putting rules about, you know, how you can label your data, you know, and things like that. While Neo4j, I don't believe it uses that standard. So, you know, so long story short, there are different products out there. I think Neo4j is great to learn. However, if you want like a, you know, kind of industrial standard production ready graph that's very powerful, that can be used in the cloud, so on and so forth, there are other products like Anzo, Stardog, etc. Okay. Somebody else asked a question. What package is used for computing the eigenvalue and what's the uplement for the matrix size? Right. So for my example, it was a very small example. We only had an 11 by 11 matrix. So it's very easy to find the eigenvalue and the eigenvector. Yes, no, I completely agree. Obviously, the larger your graph gets, it's going to be harder to do that. Totally understood. However, by showing you this about label propagation, we're going to be doing we're not going to be finding the eigenvalues and eigenvectors. This one is actually using random walk theory, and random walk is you know, it's a numerical method, and you can actually find a lot of great things that way. So you don't have to analytically invert a matrix or anything like that. So very good question. So let's talk through this example, and hopefully that will give you an idea of how to solve these problems when you have very large graphs. Okay. So okay, we're talking about semi-supervised learning, and the idea is that it's very hard, in the real world to have labeled data. I mean, it's a challenge, for any type of machine learning that you're trying to do. Labels are expensive, okay, and in the area of fraud, fraud is very rare. All right, so like let's say I was trying to find terrorist financing, okay, it's very hard because they're the terrorists out there don't get caught very much, and I really don't have a lot of labels out there where I know this is terrorism and this is not terrorism, so on and so forth, right? So I have to kind of extract all the information I can out of the labels that I have, and that's what label propagation is doing. Okay, so let's say we know that node 4 and node 6 are fraud. All right, and we know that because we did an investigation, and it came out that but through manual investigation we know they're fraud. And now we want to use that information. We want to use that information to tell us something about the nodes that we don't know anything about. All right, that's what label propagation is. Okay, so like I was saying, we're going to use random walk theory to do this one. The idea is that if I start at any unlabeled node and I just walk around randomly in the graph, what is the likelihood that I end up at number 4? And what is the likelihood that I end up at number 6? Okay. Now, if I'm walking around randomly, and it turns out that more often than not, I end up at number 4, I'm going to say that I'm closer to number 4, right? If I walk around randomly and I end up at number 6, I'm going to say I'm closer to number 6. All right. That's a concept behind label propagation in this manner. All right. Now, this is the same algorithm that Google uses for PageRank, because PageRank, that was the whole idea. That's how Google started, through this, Sergey Brin and the founders of Google, they wrote a paper about this kind of random walk. And they kind of came up with this idea of a random surfer, like a guy randomly surfing the web. And if I randomly surf the web, what web pages, would I be most likely to be looking at? And that's how they came up with Google search. Now, it turns out that, in the many years since Google was founded, they don't really use this algorithm anymore. But that was the first algorithm that Google used, and that's how they came up with better search. All right, so I create my adjacency matrix and my degree matrix very similar to before. Now, the only exception is that node 4 and node 6 are now going to be absorbing states, meaning that once I reach 4 or 6, I do not move to another node. I end there. That's why it's called a terminating state, absorbing state. Okay, so I have to make a small change to my adjacency matrix. Did I, you know what, I think I missed a slide. I actually had it before, but it looks very similar to the adjacency matrix that I had before, but I just made a small change for rows 4 and row 6, okay? And then I compute my degree matrix, same way I did last time. And then I use that to create what's called the probabilistic transition matrix, okay? And I call that T. Now, the transition matrix lists the probability of jumping from one node to another node, all right? And that's simply inverse of D multiplied by A, all right? It's actually not that complicated in our simple example. If I have 2 nodes that I'm connected to, then I have 50% chance of going to either one. Now, going back to Ken's question, it doesn't have to be 50% for each one, all right? In the real world, not every relationship is gonna have the same strength. So if I wanted a more complicated example, these probabilities would be adjusted accordingly. But again, in our kind of simple example, we assume that you have an equal chance of going to any neighboring node, all right? So then I have a transition matrix, telling me the probability. If I'm in node 0, I have a 100% probability of going to node 4, right? If I'm in node 1, I have a 50% chance of going to node 3. I have a 50% chance of going to node 4, so on and so forth. once I reach node 4, I stay there. You know, I only have a 100% chance of going to node 4 because it's an absorbing state. Now, we need to find the long-run equilibrium of this transition matrix, okay? Or its steady state, all right? So what we do is we raise matrix T to a power of infinity, and we do that, and you find that the matrix will converge, all right? And it converges, and the convergence looks like this, okay? And these are called our steady transition probabilities, all right? Okay, now note that we only have values in column 4 and column 6, all right? Now we've correctly, okay, so now I can use those probabilities to determine what my label should be for the other nodes, all right? So let's look at column 4, all right? So column 4 in row 0, does somebody have a chat here? It's not only for binary classification. So node 4 and node 6 could be any type. You know, I could say node 4 is fraud, and I could say node 6 is non-fraud. The basic idea is that we're going to assume that the nodes closest to node 4 are going to get the label of node 4. And the nodes closest to node 6 are going to get the label of node 6, but there's no stipulation that they're binary. Basically, it just whatever the label of node 4 and node 6 are. So it can be non-binary. But in this example, it is binary because, again, it's a simple example. Okay, so now you can see here that if you go to you know, row 0, it has a 100% probability of being more connected to node 4 than node 6, right? And that's obvious, right? I mean, 0 and 4 are connected, and 0 doesn't have any other connections. So why would I assign the label of node 6, you know, to 0? So we can intuitively see that, right? Now, what's more interesting is node 5, right? So if I go down, and I highlighted that row, if I go down to row 5, I can see it's giving me a 62% probability of being node 4, and it's giving me a 38% probability of being node 6, right? And that makes sense because 5 is, you know, right in the middle. But there are a few, there's an additional connection to node 4, right, through node 3, right? So if I was only using the information in the graph, I would think 5 would be closer to node 4 than node 6. And we can see that with the 62% to 38% probability. So that makes very intuitive sense, right? So, you know, our result is matching up with, you know, our visual examination of the graph, right? So you can see how this can be powerful when we have, you know, thousands of nodes, you know, thousands of relationships. It's a very, you know, quantitative way to find out what nodes are closest to me. All right. Okay, so I think that's about it. That's all I had. I hope this kind of gave you an introduction to graphs if you weren't familiar with them. I hope it gave you an appreciation for how it could be used for anti-money laundering or fraud detection. I hope that you can see how by having our data organized in graph format, you know, there are a lot of great, you know, algorithms and models that we can apply. Just simply because of the way we structure the data. So it kind of opens up a lot more possibilities, you know, to use, you know, different techniques, you know, and you know, that are very grounded in academic theory. So thank you, everyone. If you want to look at the full white paper, if you had questions or want to go through the examples again, you can find that at the FI Consulting website. It should be up. Definitely find me on LinkedIn. I'd be happy to connect with you. And yeah, I can take questions or anything else you want to talk about.
Hey, Robert, this is Simon. Can you hear me?
Yes.
Okay, hi Robert, thanks a lot. Thanks for this talking anti-money laundering and fraud. That's pretty important topic for bank. I work for bank as well. I'm just wondering, when you use the case, you will label something is known, something is known as fraud. Do you use like the OFAC as the case to label as the known kind of verified case, or any other source you can use as that's the known fraud?
Yes, you can use OFAC, definitely. But I think the idea that I had in mind here was that, you know, you have human examiners, right, at the banks. And maybe they had done some research, some manual research into Node 4, Node 6. They found out they were fraud. And you can now use that information. But there's a limit on how much the humans, right, can manually investigate, right? So the idea is that we only have partial information, you know, but we can leverage that partial information by looking at the different relationships, you know, of the different entities. And so that's the idea. That's kind of the real world parallel, right? That we have some information, but this information is very expensive to get. So now we want to extend that information, you know, by looking at the relationships, organizing our data in a graph, and by doing that, we can extract more value, you know, from the information that we have, you know, whether it be from OFAC or any other source.
Yeah, thanks, Rob.
Hi, Robert. I have a question. This is kind of a very general question. Just wondering whether the knowledge graph can capture the directions of the relationship. So, for example, like between the two nodes, are there any like directions between the two or several of them? And if so, like how do we capture it in the matrix?
Yes, right. In this example, again, we kind of assume that the relationship had the same strength in both directions. And intuitively, for something like, you know, fraud detection, I think that's an okay assumption to make. I generally use the direction more for querying, you know, so if you go back to the original example of the movies and acted in, directed in, and things like that, you know, so if you want to do a query, which is another application of knowledge graph, which is very powerful, you know, let's say I wanted to find out, you know, all movies that Tom Hanks, you know, acted in, then I would use the direction of a relationship to pull that kind of information. But in this kind of clustering, you know, that we were doing, we kind of made the assumption that the relationship is equal strength in both directions. I think that's an okay assumption for this, but yeah, so it didn't really come into play here. Yeah.
Thanks.
Hey, Robert. This is Len Yun Zhang. I work for Navy Federal Credit Union.
Oh, great.
I have a question. For this type of method, you would already have a suspect, right? Then you find all the transactions related to this account or this person, this member. It's not used for detect potential suspect from millions of members, millions of accounts, right?
Yes. So there are different things we can do. That's why the clustering and the label propagation. Clustering is an unsupervised, so we don't have any information at all about the labels, right? But for example, what you could use clustering for, you can use that to focus your resources, right? So I can get a high level view of all the clusters on my network. And then let's say I only have enough manpower to investigate, you know, X amount of cases. Then I can say I will only investigate clusters, you know, 3 clusters, you know, whatever it may be, because I only have time to investigate those. That can be a way of kind of, you know, narrowing down, you know, the you need to look at. Label propagation is if you have some information. So, you know, I worked on credit cards at Navy Federal. You know, obviously you guys have a lot of credit cards. So, like, for example, somebody calls in and they say my card was stolen, you know, and then you have information about the card being stolen, right? And then say, okay, can I use that information because somebody reported their credit card being stolen? Can I now use that information to find out if people are stealing other people's credit cards? Like maybe there's somebody who has like a skimmer or whatever, and like, you know, anyone who uses their credit card at Starbucks is getting their information stolen. That would be an example of how you use label propagation, because you might have some information, but now you want to use information to find out more about other people you don't know about. So I think for credit cards, there's a lot of similarities. And if you imagine the amount of credit card transactions that occur in a day with all your customers, you can see how this data gets very large very quickly. And I honestly can't think of any way to efficiently, you know, analyze all that data without something like a graph. So.
Thank you. Thank you very much.
Yeah.
Hey, Rob,
Yeah.
can you go back to the previous slide, the last one?
Sure.
Yeah, I'm curious in this one. In this visual presentation, I can tell that of like 4 is more close to 5 than 6. But I don't know whether this requires some kind of expert judgment, because you can draw this way, or you can place the 4 and 5 line more longer. How could you decide that?
Well, the thing is that, again, like going back to the random walk theory, right? If I just started at 5 and then I walk around randomly, I would end up at 4 slightly more often than I end up at 6. And the reason why is that I have 2 pathways to 4, right? I can go to 4 directly, or I can go to 4 from 3, you know? So I think that's the difference of 62 to 38%.
I see. Okay.
So Robert, can I have a question?
Sure.
And this is Charles. So my question is, why not using, for example, weighted graph in case people have similar questions?
Use weighted.
Yeah, weighted graph. You assign a weight on the edge, right? And then that can directly address that ambiguity.
Yes, you can absolutely use weighted connections, and a lot of people do. But you see, that requires an additional assumption, you know, that you have to make. So I wanted to keep it simple and just assume that every node is equally connected to neighboring nodes. But if you have knowledge, you know, domain knowledge about the strength of your relationships, you can definitely do that. But then you have to quantify, you know, what weight do I put, you know, so, and that can be challenging, right?
Okay, thank you.
I have another question. So this question is actually similar to Ken's question. So I was just wondering, like, because of node 3, so 5 is is closer to 4 instead of 6. But I noted there's node 1, so 3 can go to 1, go to 4. So are we going to like consider this effect as well? Because literally 5 can go 3 and then go to 4, but it can also go to 3 and go to 1 and go to 4.
Right. It's so unless the node is an absorbing state, I mean, nothing, I just continue on my random walk. Yeah. The random walk only ends if I reach 4 or 6. So again, like I just simply list out all the possible paths from 3. And it turns out that there, you know, 85% of them end up at 4 and 15% of them end up at 6. And you can see that intuitively, right? There's only one way. There are only 2 ways for me to get, well, I mean, I guess there are more if you kind of go around. I mean, but you can just kind of see that intuitively, right? I just have fewer ways to get to 6 than I have to get to 4 from 3.
Yes.
So Rob, if there's no more technical question, I wanted to.
Hello.
Oh,
Sorry.
yeah, go ahead.
Hi. This is Joe from Visa. I'm also working for fraud detection part. I'm wondering, do you have any experience combine the machine learning algorithms with your graph analysis? Could you please share some your learnings or experiences?
Yes. So in the first example that I gave, you could actually use k-means in combination with the spectral clustering. And all you would do, you would take the Fiedler vector, like I said, and then you would run k-means on it. And you don't have to use the Fiedler vector, which is the first eigenvector. you can use, you can use the next high eigenvalue if you want as well. That's what, if you go Google this online, a lot of people do it that way. Like I mentioned before, I feel like the spectral clustering, the way I explained it, is like just very mathematically correct. The k-means requires an assumption, again, about how many clusters there are and things like that. So I show like kind of the most theoretical example. But no, you can combine both approaches. You can take eigenvectors and then do k-means on those. You might have to, for very large. Yeah, so there are definitely ways to combine both approaches. Yeah.
Thank you.
Hey, Rob. Yeah, this is Simon again. So want to ask just a little bit of detail on the fraud, because fraud actually is a pretty broad topic.
Mm-hmm.
It can either from application or from the use for credit card case. It also can be like from Basel perspective, internal fraud, external fraud. So from your experience, which fraud is kind of more, these two methods have more effective, and any kind of insights why this kind of more effective?
Right. Well, I definitely wanted to show the label propagation because I feel like it mirrors like a real world example, right? Where we actually have very limited labeled data. I think fraud detection in general is a very sparse, data problem. Because again, like I said, if you're trying to look for terrorism or these very rare events, right? It's very hard to get, historical data, labeled data, so on and so forth. So I think you have to use an unsupervised or semi-supervised, type method. So I think that these techniques work very well for fraud because, we have limited data, right, in the fraud space. Unlike, say, mortgage default or something, right, where we have a lot of historical data, and we can use different techniques, supervised techniques, right? So a lot of the banks are concerned with bank secrecy or anti-money laundering, of course, AML, DSA. But really, the great thing about graphs is that it can be applied to so many different things. Right now we're actually trying to use knowledge graph for just, basic default prepayment, credit risk. It can be used for that as well. It really has so many applications. So, a lot of these concepts can be applied to different domains, and you can adjust your labels, your relationships, accordingly. So, I definitely don't want to give the impression that that graphs are, are only good for fraud, because I'm constantly amazed at how many different areas a knowledge graph can be applied to.
Sure. So follow this topic. For example, do you think or do you feel positive if this method used for kind of very routine, like a mortgage default, credit card default? How is that effectiveness?
Yeah, that's a great question. And that's something that we're exploring now. So definitely stay tuned for a blog about that, hopefully coming out, soon. Knowledge graphs have a very unique relationship with neural networks. And you'll find that a lot of the theory behind a deep neural network is actually very, related to knowledge graph. Convergence and accuracy. That's kind of really all I can say. It's a very kind of novel thing. Not a whole lot of research is done to it, but we're using a lot of knowledge graph for variable specification. Let me put it that way. Yeah.
Great. Thanks, Robert. Yeah.
If there's no more technical question, I want to have Rob to briefly talk about data science career, especially in the DC area. I know Rob has been a people manager and the data science lead at FI Consulting for many years, and then Rob has interviewed quite a lot of people. So I want to ask, what is your hiring principle for data science role or model validation, model development role? And
yeah, yeah, I can talk about that. But there's so many amazing people on this call that I hope I don't say anything wrong. But I can tell you about what we do at FI. So FI is kind of unique in that we're consultants. So the kind of data science we do is very client oriented, right? So our mission is to solve client problems, and we have a very wide variety of clients and a very wide variety of problems that we have to solve. So I would say to work at FI Consulting, you have to be very flexible. It's important to know a lot about different techniques. It's very important to be familiar with several different types of programming languages because you never know what kind of technology the client has. And we do our work in a very public way because we have to constantly be in meetings with the client, explaining what it is we're trying to do, giving presentations, so on and so forth. So I think it's very important to explain very complicated technical knowledge in a way that is easy for people to understand. Because frankly, a lot of our clients don't really have, a lot of clients in the federal government in particular, they might not have the same level of statistical background that you have. So that kind of communication, I think, is very important. But I think we're looking for the same things that a lot of people, in your organizations, Fannie Mae, Navy Federal are looking for. Obviously, skill set is very important. It's very important that you have a strong background in like probability and statistics, econometric modeling, multiple linear regression, and programming. Programming is becoming more and more important because, we have to find the data, you have to prep the data, and to do that, you have to use a lot of, programmatic, data mining, type techniques. And then you build the model, of course, and you can build it like in Python or R, using these kind of statistical packages. But then there's another part that's kind of overlooked. A lot of times we need to deploy our model. So we need to implement it on some type of production platform. We need to make the model into a web service. We need to make the model into a reporting type function where you can kind of run the model, periodically, get results. So it's very important that you have a strong theoretical background, but I can't emphasize enough. It's very important that you have a strong programming background as well, for all the reasons that I just mentioned.
Okay, great. So also, this year kind of very special for job seekers and new graduates. So I don't know if there are any major change at FI Consulting in terms of hiring standard or number of headcounts, and also have you observed some major changes in the DC area in terms of
well, yeah, it's a very strange time right now. Yeah, it's I got my master's in 2007, so there are a lot of parallels to the financial crisis, I believe. FI Consulting, we're hiring. The reason why is that we have a lot of work through the government, support for COVID. So we do a lot of work with Treasury, and we're doing a lot of work with the CARES Act, which is stimulus, and these, government-backed loan programs. So we need people to help work on that. We do a lot of work for SBA, and we're doing a lot of work on their Paycheck Protection Program. So FI was, fortunate that, we're able to work on these projects that are really, quite complicated right now. So we are hiring. But I'll be honest, and I'll say that the competition has increased since COVID. you know, there are some, you know, job separations, obviously. And I definitely find that the caliber of our candidates has increased. So, you know, it's a challenging job market. So, yeah.
So you're not now you're more picky than before, right?
You know, maybe I'm constantly impressed now at the caliber of people who are applying to the company. Yeah.
Okay. I think there is a question in the chat box. People are asking.
Yeah, that's a great question. You know, a few years ago, I would have said equal, but I mean, to be honest, I really think Python is overtaking R. The reason why is that there are just so many more extensions to Python. You know, like I was mentioning before about web services, deploying your model in the cloud, like AWS, for example. If you want to do things like, you know, knowledge graph, you know, I just think there are just more packages in Python. I always go to Python as my first option, unless I'm doing something very quick that I know that might be faster in R. Like if I'm doing a very quick analysis, I might use R. Just because I like ggplot and it's kind of simpler to make quick plots in R than in Python. But I really, yeah, I just think Python is better in terms of documentation, you know, on the internet, more of like the blogs, you know, where people have ideas and the code available in GitHub and things like that. You'll find that a lot more of it's written in Python than R. So that's my personal preference. Yeah.
I think there are still many government agencies that still require SAS programming. Is that right?
Yeah, that's definitely true. Nowadays, the only place I ever use SAS is federal government. Capital One has completely eliminated SAS. They got rid of all their SAS legacy models. I know Scott Hallworth at Fannie is doing the same thing at Fannie Mae. Freddie, I think, still uses some SAS. But you know, Navy Federal probably has a combination, right? But every year, you're going to see less and less SAS. Even the federal government, they have a lot of legacy models in SAS, but they're more open to using Python and R, especially when we work for Treasury and like the Federal Reserve. Those are very kind of forward-looking institutions, and they'll use more open source.
Okay, great. Are there any other questions?
Yeah, another one in the chat. Best practices to build a graph from relational database. Yeah, you know, I wish I had my colleague here. He does more of like the data ingestion for a graph.
We will invite him next time. Who are you talking
Yeah,
about?
Greg.
Okay.
Greg is kind of the product guy. He really knows a lot about, he works a lot in Stardog and all these advanced products out there. And he'll tell you the best practices to, you know, migrate a database from relational to knowledge graph. But let me try to get back to you on that one. If you connect with me, then we'll be connected and we can follow up.
Cool.
Okay, let me just put my information back up there. Please go to the website and download the paper and find me on LinkedIn. Thank you so much, everyone.
Thank you, Rob.
Thank you.
Thank you.
Okay.
Thank you, Robert.
Richard. Hi, Richard.
Hey, yes, sorry I was on mute. Thank you,
have-
Rob, for the excellent talk. It was very interesting.
Sure. Thank you.
Wendy, do you want to touch on the sponsorship a little bit? Or Jidong, you want to talk about the membership?
Sure. Yeah. This is Jido. So yeah, maybe let me take a few minutes to give people status update about the CADSEA membership. I think really appreciate the technology team's support. Our website, CADSEA.org/membership right now is open to register. So people who interested on become the member, please do so. So after becoming the member, you can see you do not need to pay any actual cost to attend any kind of a similar event like today and going forward for 12 months. So I think today's talk, Rob, thanks a lot. That's really interesting, really critical topic in the banking, and also it can be widely applied to other industry as well. So yeah, for people want to become the member, please go to website. For student, we do have the big discount. For professional, we decided to charge the $35. Student is $20. So yeah, if any question, please reach out to our CADSEA, the membership volunteer team. That's all. Yeah, back to Richard.
Oh, that's great. Thank you so much. I really looking forward to have more and more members joining CADSEA so that we can build up this community. We do need some amount of the fee so that we can provide enough and sufficient financial support to make this organization grow bigger and stronger so that we can provide more and more good talks and other activities and programs to help everyone to build up the experience and the network. So it's really a crowd effort. It's not on any single person or individuals because this is a community. So really appreciate all the support and volunteer from everyone. Ken, do you have anything else?
Sorry, I muted myself. At this time, we haven't decided our next event, but we have quite a few lined up. So we will sort them out, and then maybe I think sometimes in August or early September, we will have another forum.
Great,
Yeah,
thank
keep
you.
tuned.
Thank you, everyone, and wish everyone has a good afternoon and the rest of the day. I'll
Bye.
see you next time.
Bye.
Bye bye. Thank you.
Thank you.
Thank you.
Bye.
Bye.
Thanks, bye.